Thank you for the introduction. And I'd like to thank Canva Resources for providing the samples I used in this project and allowing me to share all of this data. And also, I'd like to thank the people at the Natural History Museum and Imperial College for their guidance and teaching me how to use the instruments featured in this report. And also, big thanks to everyone here for both in person and online for agreeing to attend a presentation about sand. Now, that might sound a little bit unusual, but this is exactly what the project and this presentation is about. What you can see on this romantic-looking picture is one of the dredging operations at the Moma titanium mine in Mozambique, which is currently excavating a heavy mineral sand deposit on the Indian Ocean coast of Mozambique. What that is a type of placer deposit. So basically a bunch of heavy mineral, well, as you can see, basically a beach that's full of, other than sand, heavy mineral grains, which were transported from the hinterland via rivers, dumped into the ocean, and via wave action formed into this huge stretch of sand with valuable titanium minerals. Okay, but what exactly was the purpose of the project? Well, as you can see on the graph on the right produced by Canva, ilmenite is the most important mineral recovered by the plant. And ilmenite is about 52% titanium by weight, and within this big body of sand, within this resource, a fraction of ilmenite with TiO2 lower than 52% was found. And basically, my task was to figure out what caused the lower titanium in this fraction, which could be caused by basically two things. It's either that there is a separate low titanium mineral or minerals that are being transported into the into the ilmenite concentrate and driving down the titanium concentrations, or that the ilmenite itself, the grains of ilmenite themselves in the mineral structures, they have less titanium metal. And once I knew the answer to that question, well, I'd like to say maybe say something about how this titanium dioxide concentration might be increased. And so I'd like to say a few things about the workflow that I used to figure all of this out. But first, we had to get the samples from Mozambique and process them before they were shipped to the UK. And so this process was mostly focused on things that relate to the fact that it's sand. So they had to get rid of all the quartz and other non-magnetic minerals and get rid of size fractions that were either too big or too small. And then all of this material was taken and put submerged in this organic resin in the form of pucks and transported to the UK. And so what I used to analyze the samples is the TASCAN TIMA SEM. And basically what TIMA does is it produces this high resolution interactive raster image of the samples where each area is assigned with the measured EDM spectrum on that sample. And later on with the program, each pixel that's produced in this manner is assigned with an identity, basically a mineral type that's defined by the user. And basically how that works is it's kind of a checklist of minerals that you give to the program. So basically, you say the first mineral on your list, you have a range of spectral peak heights that you've specified for this specific mineral, and say when the program is identifying that specific pixel, it looks at the first entry on the list and it checks all of the elements that you've specified for it, whether the spectral peak heights are within the range. So in this case, it looks at the iron peak height and it's within the specified range, but it looks at the silica and it's lower. So it moves down to the next position on the list, looks at the prerequisites specified for that one. If it doesn't fit, it goes down goes down the list, goes down until it finds a mineral which fills the prerequisites. And so, as you can see, the order in which the minerals are featured on the list is also important. And so this is what the program produces. As you can see, all of the different grains have different colors, which corresponds to different minerals. All of those white boxes are grains of interest, which I analyzed in further detail. But generally, green stuff is iron titanium oxides, so the good stuff, and the red stuff is iron oxides, or I should say iron-rich minerals, because we also have ovospinel in there. And in some of the blocks, they account for over 6% of the volume occupied by all minerals. So that's somewhat significant. But, well, is that accurate, though? Well, I think it mostly is. So mass balance calculations that I did. So basically, the process was I asked TIMA to calculate the composition of each sample block, the elemental composition. I then, on the base, I then took the model mineralogy and calculated the composition based on the model mineralogy using stoichiometric compositions of the different minerals and actual average compositions of the minerals in the samples calculated by the TIMA. And so, as you can see, if we use average compositions of the minerals in the samples, we have maybe on average about 1 percentage point too much of iron and about half of that of titanium. So maybe iron and titanium rich phases are slightly overrepresented, but that's a margin of error I'm comfortable with. And conveniently, this matches the titanium dioxide concentrations in the ilmenite fraction from the specific resources within this vast ore body that we're investigating. So if you take all of the iron oxides and the ilmenite, put them into one fraction, we're talking about material from these concentrates, it matches the ilmenite fraction that they're seeing from these specific areas in the actual mine. And so the processing steps at the plant, well, that's why are all the iron oxides getting into the ilmenite concentrates? Well, what I didn't mention previously is that what's used to separate ilmenite out from the concentrate is magnetic separation. So magnetite and titanamagnetite, yeah, they're magnetic, so they're going to even more magnetic than ilmenite. So they're going to deport to the ilmenite fraction. But what about ovospinel and magnetite? Ovospinel and hematite. They're not magnetic, not in these conditions. So what and how do we tie that with how we might want to remove these iron-rich minerals? Well, as it turns out, a large proportion of the iron-rich minerals, really most of them, as you'll see, can be described as composite. So, well, the grains can be described as composite. So as you can see on this figure, this grain in the red, it's titanamagnetite, and in the green, it's ilmenite. And the same goes for all of these here. The brighter areas are titanamagnetite in all cases, and the darker ones are iron titanium oxides. And so how many of these grains are actually monomineralic? Because that would make them easier to separate. Well, as you can see on this graph, approximately 60% of the volume occupied by iron-rich minerals can be found within grains consisting in over 70% of iron oxides. So they tend towards the more, overall, they tend towards the more iron-rich side of the spectrum. And this And on this graph, it might be a little bit easier to see. You have how to read this graph. You have a grain that's 51% titanomagnetite, so it belongs to this class, and this class accounts for approximately, in this sample block, approximately 5% of the volume occupied by iron oxides can be found within grains belonging to this class. And so they're, as you can see, they're a bit shifted towards the more iron-heavy side. Well, what is causing this? It's most likely just the mineralogy and the igneous processes taking place in the protolith during its formation. So basically, I think it's got to do with the ulvospinel magnetite solid solution, which during cooling undergoes oxyexolution. So basically, it separates out into magnetite and ulvospinel, and ulvospinel oxidizes into ilmenite. And so you have this igneous texture of interlocking ilmenite and magnetite minerals, which are then, during weathering, broken up into these tiny grains, which make their way onto into the deposit. And so, what are our options for separating these iron oxides and ulvospinel from the concentrates? As you can see, the more monomineralic iron oxide grains are actually smaller on average than grains in less iron-rich classes, which would make them easier to separate. However, that's really a small fraction of all grains. The smaller grains, the smaller composite grains, tend to be in the lower classes. So we have to also remember that their properties will be mixed. So we could potentially just do a rerun of the magnetic separation step to first get rid of the magnetic minerals and then separate out the ilmenite. Or, but that's likely to leave all the lower classes in the concentrate. Potentially, we would have to look at a method that's based on some other variable, like density. But that's material for a different investigation. Okay, thank you very much. I'd love to hear your questions.